should know that these questions that I'm going to go over are the most important ones for your review. So make sure that you will definitely get every detail about it. So let me go ahead and share my screen. I have a few questions here. Okay, here is our first question. I think that you guys are seeing my screen. If there is anybody who's not seeing it, let me know. So as you see in the first example, the following figure in part 1, you should change the circuit to a common emitter amplifier and find its voltage gain. In the second part, you should change it to a common collector amplifier and then find the voltage gain again. First of all, when you have any circuit, you'll try to do a DC analysis to get GM, RE, that level RE, and current of the collector. So let me go ahead and do some DC analysis on this circuit. So for DC analysis, you know that all the capacitors will be open circuit, so there will be no more in our circuit, and I will have this guy, I will have this, then here comes a transistor, okay, so resistance in collector is 3.3 kilo ohm. Here we have 3.6 kilo ohm. The bias resistance are 100K and another 100K. So as you see here, this is the bias for the transistor. We can simply turn this bias to a voltage source and an equivalent resistance. So for doing this, you need to do Thevenin Norton. Simply, if you just do some voltage division, you will find the voltage of this point. So voltage, imagine that this is Vx. Vx will be 100K over 100K plus another 100K, this is voltage division, times the voltage, the VCC voltage, which is 5 volts. Okay, and so you can either find this using Vx equation. So you can either go this way and find your Vx equation, or you can use Thevenin Norton method. In the Thevenin Norton method, I'm going to just draw the equivalent circuit and just show you how it looks like in Thevenin Norton. In Thevenin Norton, you know that we have a 5 volt voltage source. So that will be our 5 volt voltage source. Following with that voltage source, there is that top 100K, talking about this, a top 100K in series with the voltage source. And then they are connected to another resistance with one common node, and the other node will be the ground, like this. And here goes the transistor and the rest. So I know I can do something here. I can apply Thevenin Norton, and actually I can convert this voltage and resistance to a current source and another resistance which will be parallel with this 100K which we have here. So simply, if you just apply Thevenin Norton from here and convert that to a current source, so your current source will be 5 divided by that 100K. So 5 volts divided by that 100K, this will be the amplitude of your current. A parallel resistance of 100K and one parallel resistance which you already had before. Like this, and here goes the rest of the transistor. Now simply you can see that we have two parallel resistance, you can simplify the equivalent, and we know that 100K parallel with 100K makes it 50K resistance. So if I continue this here, finally I will have this 5 over 100K as a current source. I will have a parallel 50K resistance, and here comes the transistor. So this is the Norton equivalent of the circuit. Again, from Norton to Thevenin, you can do some conversion. If you try to convert it back to Thevenin and have a voltage source instead of a current source, I need to do one more step here. So for doing Thevenin Norton, you need to find the voltage coming on both ends of this current source. So that will go like this, and the voltage coming all the way up to, or you can either find the voltage on both ends of the resistance. You know that the current will pass through this resistance, so it will be the current times the given resistance, and that will give you it's like 5 over 10, 100K times that resistance. And then you will have the equivalent resistance in series connection, and then you will have your other, the transistor and the rest. Finally, by doing this, you can find that voltage source to become 2.5 volts. Follow where we start, where we headed to. We started from a simple bias, did some conversion between Norton and Thevenin, and end up here, and that's just super easy. And you know that just instead of doing all this Thevenin and Norton, you could simply do some voltage division, and in that voltage division, you could do something like finding the voltage of Vx, and again, if you do the voltage of Vx, that will give you 2.5 volts. And then your equivalent resistance will also become, would become 100K parallel with another 100K, and that will give you 50K. So you could either do this green way or the purple one, but the purple one is most desired when somebody is grading your papers. Thevenin Norton is mostly desired. Okay. Finally, we are done with finding the equivalent Norton, Thevenin, and Norton. And now here I'm going to complete it with the rest. Remember that on the top on the collector I had a 3.3K resistance, and here I had a 3.6K resistance. And I have a voltage source of 5 volt on the top as well. Simply, our job for DC analysis is to find that little RE, GM, or IC. Okay, let's go ahead and find that, if you can find I base, and then you can simplify IC. Just remember, the question didn't mention it, but we will take beta as 100. Simply, if you just do KVL in this loop, you can simplify I beta and then relate I beta to I collector and the rest. So let me write down the KVL in this loop. This is my KVL in this loop, so I will have negative 2.5 plus 50K I base plus a base emitter voltage plus 3.6, plus 3.6K IE equals 0. Remember, when beta is a great number, we know that usually IC is approximately equal to IE. So remember this, and if you find IE, it's like you have found IC. Okay, from here, and I know that there is a relation between IB and IC. Let me show you. There is a relation between IB and IE. Simply you can say IB equals IE over beta plus 1. If you just replace IB with the given equivalent on the top, you will have negative 2.5 plus 50k IE over that plus 0.7, taking the base emitter as 0.7, plus 3.6k IE going to 0. So doing some rearrangements, finally you will find your IE like 0.44 milliampere. This is your IE, and simply, you can claim that your IC will also become 0.44 milliampere. Now our next job is to find that little RE in the AC model of the transistor, and that little RE comes with VT over IC or IE, they're both fine, over 0.44 milliampere. And finally, that little RE will become 56.8 ohm. Now, when you have that little RE, you can go ahead and find GM. And your GM equation will be VT over, IC. Yes, it will be IC over VT, sorry. It will be IC or IE over VT. And again, IC is as great as IE. VT is 25 millivolt. Finally, you will have 0.0176 as your GM. So our goal of doing DC analysis was only finding IC, GM, or RE. Now let's go ahead. Let's go to the first part of the question and try to convert this given figure, to this given circuit, to a common emitter amplifier and find its voltage gain. We know that when it wants to go to a common emitter, it means this capacitor on your emitter will, in AC model, all the capacitor will be short circuit. So instead of having something like a capacitor here, you will only have a simple piece of wire. I will later on check the chat box. Let me first finish this. So for finding the common emitter here, I'm going to set the VO1 equal to 0. Why? Because we want to have our emitter connected to the ground. So continuing this, I think I need to write it down here. So here is the first part of the question. I want to try to do common emitter. For doing this common emitter, I'm going to put that V output 1 equal to 0. Then our emitter will be connected to the ground. Then finally, in our AC model, and remember this is our AC model, or AC analysis, there will be some, if you just take a look at it one more time, in our AC analysis, this first capacitor on the left will be a short circuit, then VI will come into the circuit, the O1 will go to 0, then it means from emitter there will be just a ground, and the top capacitor will also be short circuited. It means your output will be from collector. So continuing here, I have this, which is my VI. I have, all the current voltage, all the voltage sources and current sources will go to 0. But DC sources actually. We have something like this, and then I have a RC resistance, which is 3.3K. Our emitter goes to the ground, directly connected to the ground, and I will have here as VO2. This is actually where you need to find voltage gain against VO2 against VI will give you the voltage gain. Again, simply, you have something like this, and you can either do some, you can either simplify this circuit by doing 100K parallel to another 100K and doing some more Thurman Norton here, or just simply go ahead and find VO2 over VI. Listen, VO2 over VI, I have a common emitter amplifier. In this common emitter amplifier, when we have VO2 over VI, it is the Hawaiian dance method. And the Hawaiian dance method, I know that it will be all the resistance in the collector over all the resistance in the emitter. So it will be something like something over this. All the resistance in the collector will be only 3.3K over the resistance in the emitter. As you see, there is no resistance except that little RE. And that little RE was 56.8. Oh. And if you find this, finally, you will get a negative 55, almost negative 55, as the voltage gain of this common emitter. So that is all about part 1 of the question. We're almost done with part 1. I think the number of questions are getting higher. Great. Okay. I'll be back with you guys. If you have any questions, please raise your hand in the queue, and then later on I will open the queue and answer to all your questions. Let me finish part 2 as well, then I will be back with the queue and answer to each and every one question here. Okay, now I need to do the part 2. In part 2, you have the amplifier, and you have to convert it to a common collector amplifier. Common collector amplifier and find its voltage. Remember, when you are talking about a common collector amplifier, it means now when all this capacitors are open, are short circuit, you need to set VO2 equal to 0. Then it's like your collector will be connected to the ground. If the collector will be connected to the ground, then here will be your output versus the VI on the left, and then finding the average, the voltage gain. So let me show you the equivalence. I think I need to insert one more page here. So let me continue here. This is about part 2 of this question. In part 2, when you're trying to find the common collector, I will set the VO2, which was the output, and the collector equal to 0, means will be connected to the ground. Then our AC model, AC analysis, will look like this. Again, I have positive and negative VI. Instead of that 100K and 100K parallel together in the top, I'm going to show it as like 50K parallel to VI. So here it will go like 50K. Then I will have the transistor here. Collector is connected to the ground, but you have emitter resistance of 3.6K, and this point will be your output, VO1. Then, even before doing this voltage gain, we know that when we have a common collector, our AV, our voltage gain, is almost 0. But we can also show it in terms of the equations. It will be always something around 0, something around 1. Sorry. So our AV here means VO1 over VI. What does that mean? VO1, if you pay attention, VO1 is the voltage over that RE, that capital RE in the emitter. So it will be 3.6K. What about VI? VI will be the voltage. You see, VI is here. If you follow this thread, VI is here. VI is the voltage over that little RE and then that capital RE. So simply you can say it will be that little RE, which was 56.8, plus that capital RE, which is 3.6K. Because this 56.8 is pretty negligible compared to a resistance in kilo ohm, then you will just consider it to be 3.6K over 3.6K, which is almost 1. So the answer will be, if you want to find it accurately, actually, I have the accurate answer as well. Find it accurately, it's like 0.98, which is pretty close to 1. Now let's go ahead and find your question in the Q section. Okay, I have many students here. Soban, please go ahead.
Yes, I had a question for like part one where we're looking at the common emitter.
Yes.
So in the past, we've like shifted any resistances on the base to the emitter using the resistance reflection. So why didn't we do it here with those 200K ohms?
Those 100K ohms are the biasing. Okay. When you see, when you want to find VO2 over VI, do you agree that VI is connected to base directly?
Oh,
So
yeah, I
it's like
see.
VI is here. You even don't need to
Yeah,
include all those biasing resistance.
okay, I see. So the 100Ks, they don't affect the VI, so that's why we don't
Exactly.
include it.
If those 100K was something like, if it was in series, then you would have to do it. But it's in parallel. When
Got
it's
it.
in parallel, means VI is directly connected to base.
Sounds good. Thank you.
You're welcome. So the next one we have Aiden. Aiden, please go ahead.
Yeah, I just had two quick things. One, in part two, if you scroll down for a moment,
Yeah.
do you not have to? So do you not have to bring the RE, the little RE and the big RE past the? I think I might be asking the same question, but
Yeah.
past the VI. Or
You see, as I think I
like,
just
are you getting the
said,
core voltage gain? Sorry, when you do
sorry.
this, are you getting the core voltage gain when you do this for the CCC? No, you're not, because you would not have VI then. Don't you have to include the 50K because you're not getting the core voltage gain, so you'd still have to do technically.
No, because this is a core voltage gain. You see, VI is connected directly to the base. You don't need to include this.
Oh, because it's parallel, yeah.
Yeah, it's just in parallel. Again, if it were in series connection,
Yeah,
then
it's
you
not
would have
Bayesian.
to
Okay,
bring
yeah.
it to the emitter or like include it somewhere. But
Yeah.
it's not connected anywhere.
Okay, yeah. No, I get
Just
that bit
ignore
now. Just
it.
the last bit being that, wouldn't you technically want to do the resistance reflection rule for the R? Do you need to do the resistance?
Usually, you see, it depends. If you have, for this example, let's talk about this. I know that that little RE is already in the emitter. Okay, so I have something else in the emitter as well. And that would be much easier if you just keep all the resistance in the emitter. But if you had something like this, for example, a voltage gain, you had another resistance in the base, and then you had something like this, um, like an emitter, a common emitter, then you know that you have a little RE in emitter, but another resistance in your base. Then it's better to do some resistance reflection, and instead of RE, work with R pi and bring this RE up onto your emitter, onto your base. But now it's not necessary here. It's just some extra work to do.
Okay, and
And not needed.
the voltage at the base, though, I thought was going to only feel, would have to feel the R pi and R, I'm going to say RE3 pi, I thought it had to actually feel the resistance in the equivalence pi region because it was going from the voltage of the base and not the voltage of the emitter. like for the
If you
in for
simply
the
write,
input
if you
resistance.
simply write an KVL here, you will find that here IE is included, and then actually I think that I didn't get your question there, Belle.
Like
But
when you're going for your when you're going for your input resistance here,
mhm.
because the like you were saying, the IE is felt on the RE and big RE. Don't you need to have them on the R pi side regardless, because you're getting
Oh, yeah.
because you're looking for the input resistance from the point of the base, not from the point of the emitter.
Yeah.
So wouldn't you have to times if that bottom VI is connected to R in, is it not supposed to be the RE?
If you were looking at R in here, yes, you should bring RE up to the base, and then it will become RE times 1 plus beta, which is R pi. If you were looking from base, yes, you would have to bring everything back to the base. I think we can continue with the rest of the questions in our office hour, guys, because I have so many more questions to go. Let me see. I have just one more person here. I need, if you want, you can go ahead if your question is a short one, because I have so many more questions to go.
Yeah, it's actually a short one. I'm
Yeah,
just
go ahead.
confused how you got VI as 56.8 plus 3.6. VI the same
Yeah,
page.
here.
VI is connected to the base, right? There's a
Yes.
voltage we're looking at the base, right?
Yeah.
And then we'll be also having a voltage drop of VBE.
No, this is not This is not DC analysis. This is AC analysis. In AC analysis, you don't have that VBA anymore. In AC analysis, you have VI, you have a resistance, equivalent resistance little RE in the emitter and the capital RE. And VI is over both of them in series. So it will be R little RE plus a capital RE.
Okay, I got it.
Yeah.
And so basically, small RE is above VO1, right? It's not below VO1. Small
Yeah.
RE.
That little, yes, that, imagine that little RE always imagine always in this part of this transistor.
I
This
got
is
it.
a big
Thank you.
I always
Thank you.
know. Okay, so let's move on to the next question. We have so more questions, so many more questions to go. So listen, this is one more important type of questions which you may face in your midterm exam. So in this question, it says for each emitter degenerated differential amplifier shown in the two following figures. So this is part A. Later on, you will have another part B. Find the differential half circuit. First of all, find the half circuit. Derive expressions for differential gain AD and differential input resistance of RID. And then for each circuit, what DC voltage appears across the bias. It means we're talking about that VCM. This is your DC, and you know that this is the AC part. What is that VCM appearing on the bias current sources and in the quiescent state when the ID equals to 0? Hence, which of the two circuits will allow a larger VCM? Now, first job is to do the half circuit, then finding the AD, RID, and then finding VCM in each of these part A and part B. So, first of all, let us begin with the half circuit. That's pretty easy, you know. Drawing the half circuit here is an easy job. But listen, that you will definitely have a question like this in your test. I'm not sure, but this is why Dr. Namner was very, he put a great emphasis on it. So this is your RC, and just you have to break it like this. This part will be simply your half circuit. So you will have RC, then you will have here, you have your, listen, your half circuit will be always shown in AC analysis. Okay, so you know that in AC analysis, that current source will be an open circuit, VCM, which is a DC voltage source will go to 0. Then you only have VID2. Then you will have RE, and here you will have 0, the ground. This is your half circuit. So we showed it all, and remember, if you're working on a half circuit, then your VOD will be also broken to half. So here you will have VOD over 2. So continuing this, I need to find the differential gain and RID. So for finding differential gain and RID, again, I will need to use with the whole circuit, not with the half circuit. But again, finding AD and RID means the input resistance and the voltage gain, you will need AC analysis of the whole circuit. So finally, you will have RC. You will have your transistor. Let's take this guy as Q1 and this as Q2. So you will have your Q1 connected to the ID2. This will go by RE. Here one more RE. And on the top again, connected to the ground, RC, Q2, and this guy. So this is our Q2, this is our Q1. Again, this body will be connected to only negative VID over 2. So finally, for finding your AD, you can simply take this differential amplifier and show it like, instead of having a positive VID2 and a negative VID2 on the other side, you can simply connect them like this. You can say that, yeah, they are also connected. If they are connected, then the voltage here will be simply VID instead of VID2. Then you can, that if this is your VID, according to the given circuit, here is VOD. For finding AD, differential gain, you need to find VOD over VID. And if you want to find your input, RID, input resistance of your differential amplifier, you can say that your the RID will be the voltage here over the current which will pass from this. Actually, it's like you are looking at this whole differential amplifier from the base of Q1. And in the base of Q1, if you do the current analysis, you will have an I base. And here you will have IC, here you will have IE1, IC1. Here you will have IB2, IC2, and IE2. Simply, your RID will be something like the total voltage over the current passing through the base of Q1, which is IB1. Okay, let's go ahead and find everything here. For finding the first one, AD, let's do first some current analysis, because I have to connect every parameters from the left transistor to the right one. Guys, you know that if this is all a differential, if this is all like a differential amplifier, then IB will be if this is IB is the total input current, then it will come out from the other side of this loop. Then the relation between IB1 and IB2 will be they are inverse of each other. They are opposite in sign of each other. So you can simply say that IB1 must be negative of IB2 because they are all in a loop, a like we are showing two opposite direction currents. And if that's so, for finding IB, according to Ohm's law, for finding current, you need to divide voltage by the total resistance, which you can see here. Oops. So finally, you can say the total voltage in this loop, guys, I'm talking about this loop. The total voltage you can observe here in AC model will be, you can simply say VID, that total VID, or you can say positive VID2 minus negative VID2, and then finally you find the same VID. Well, I'm just gonna stick that. So you can say it is V, okay, so let me write it. VID2 minus negative VID2, which is the same as totally a VID, over all the resistance which you can find in that green loop. So what are the resistance here? Definitely there is a little RE here, a little RE here as well. They are all in the emitter of the Q1 and Q2. If you want to find it, if you're looking at it from the base of Q1, you have to take it all to the base. Then I know that there are two little RE and two capital RE, so I'm going to take out that 2 as a factoring. I have this in this green loop, and I'm going to bring it up to the base because I'm looking at it from the base. Then it will be times y 1 plus beta. Finally, my IB, my IB1, which is a negative of IB2, will become something like VID over 2 times RE plus the capital RE times 1 plus beta. So far we just found our IB. We know that when beta is a great number, then you can also assume that the current in emitter and current in collector are equal to each other. So let me continue here. I can also say that, just look at it, IC1 is here. This should be exactly in the opposite of direction of the other one. If you consider them all in a loop, it means IC1 is negative of IC2. And same for IE1 and IE2. So finally, I can say it is IC1 negative of IC2. What is the relation between IC and I base? I know that the IC is alpha times I base. So it will be alpha times IB1. So finally, you can say it is VID alpha over 2, 1 plus, it will be beta times IB1. It will be beta times IB1. So having one beta here and replacing IB1 from the top, 2 RE plus capital RE times 1 plus beta. Guys, you know that beta over the 1 plus beta equals alpha. So you can again say that it's like alpha VID over 2 times of RE plus the capital RE. So this is about IC, and you have something like IE1 equals negative of IE2 as well. And that will be equal to, that will be also equal to, IE. What is the relation between IE and I base? It will be times 1 plus, it will be times 1 plus beta. Times 1 plus beta IB1. Okay, so if you times it in 1 plus beta, then this 1 plus beta and the denominator of IB1 will be gone. then you will have only VID over 2RE plus the capital RE. Okay, finally we are done with all the AC analysis of the circuit. Remember, in differential amplifier, you should always do the AC analysis on the currents. Always, that's a must. Okay, now let me continue with finding VOD over VID as the voltage gain of this differential amplifier. Guys, VOD is, okay, so let me name this guy VO2. Let me name this point VO1. This is easier. Then VOD is the differential, it's a potential differential between VO2 minus VO1 over VID. Then what is VO2? VO2 is the voltage over, let me clear this part, you will see better. VO2 is the voltage over RC. But remember, it should be in the opposite direction of IC2, because you have to, for finding VO2, you have to times RC by a current passing through RC in that yellow highlighted arrow direction. Then that means it will be negative RC times IC2. So it will be negative RC times IC2 minus, what is VO1? Again, VO1 is the voltage passing through the RC on the left collector, but it should be times with the current passing towards the ground, which is opposite of IC1. Then it will be negative. Again, that will be times negative RC IC. Yeah, I think I'm right. IC1. Let me check one more time. Yeah, I think it's right. Over VID finally. Okay, let's do some rearrangements. Taking out one RC here, then I will have RC IC1 minus IC2 over VID. And now, what is the relation between IC1 and IC2? Guys, we know that IC1 and IC2 are equal in size and opposite in direction. Then instead of IC2, let me plug in IC1, negative IC1. Then you will have 2 times of IC1 inside that bracket. So you will have 2 RC IC1 over VID. And what was IC1 from the equation here? IC1, we found this for it. So instead of IC1 on the top, I'm going to replace that alpha VID over 2 RE plus capital RE. Then finally, it will be 2 RC VID times alpha VID over 2 RE plus capital RE. Out of here, you can just do a lot of simplifying, and VID are all gone, and finally you will have alpha RC over RE plus the capital RE. This is the voltage gain in this differential amplifier. So after finding this, our only job is to find the input resistance from the base of collector 1. So let me go ahead and replace everything. So VID is the same as VID. Instead of IB1, I'm going to replace it by this. So that will be VID over 2 times of this. Then just simplifying, you can cross out that VID on the top and bottom, and then finally you will have 2 times of RE plus this times 1 plus beta. This is it. This is the input voltage, input resistance from the base of Q1. Okay, any question here? Let me see. So there is no Q here. So Aniket, go ahead, please.
Yeah.
Oops.
So for the current, so for the current in the emitter, we multiply that by 1 plus beta for the current. Like we divide that by 1 plus beta, right? If we need the resistance to the emitter.
Yeah.
For the is that the opposite way for the current?
Yes. It is.
Yeah. Okay. And another question.
Yeah.
Just scroll up if you can. Uh, yeah, over here. Why are you taking the current direction above? Like when calculating V01 and V02.
Yeah,
Like
I get it.
why not down direction is okay?
Because you for finding the O2, okay, you know that the current should go from the higher voltage to the lower voltage. So if you want to have this voltage as a positive one and not a negative VO2, you should have this point minus this point over RC. So as you see, the current direction is going high, going up. You get it?
Okay. Since the initial direction was the other way around, like
Yeah,
initially it was
exactly.
flowing
That's
from
why
zero
we have,
to that. That was okay.
yeah, that's why we have negative RC times the IC2 direction, and that negative comes from the change from the direction of
Direction, yeah.
IC2 to what we already want here.
Change from the direction, right?
Yeah. Okay, so let's see. Do we have anyone here? Soban, go ahead, please.
Yes. So, from my understanding, you can use the circuit to find gain, and it'd be equivalent to the full circuit. But could you not
Okay.
have used the half circuit and used like Hawaiian dance?
No, unless you are asked to.
Oh, okay.
Yeah, just take the whole circuit for the AC analysis.
Alright.
Thank you. Okay, next one we have Aiden. Aiden, go ahead, please.
So you're just to repeat what you're saying there. So you would recommend not then using the half circuit for this one? Was it still possible to use it, or
If the question allowed you to do it, yes, you're allowed to use it, unless you're not.
okay?
You should take the whole circuit.
Right, and with this, when you do IC2 minus RC IC1,
Yeah.
You have both arrows going in the same. Why is that exactly? Sorry again, if you could just.
I just explained it to your friend. So when I'm explaining, if you listen, then you will not have to ask a repetitive question. VO2 is here. Okay, for finding the voltage of VO2, there should be a current passing through the RC to the lower potential, which is the ground. Then that current is in the opposite direction of IC2. That negative comes from here.
Okay. Yeah, no, that makes more sense. It's just because you had previously, you had both arrows for both sides going upwards rather than one going downwards and one going upwards.
I was just explaining VO2 and VO1. So same stuff happens here as well. For finding VO1, you should have a current passing through RC to the ground, and that yellow current on the left is opposite of IC1. That's why this negative show up.
Okay, that makes a lot more sense. Thank you.
You're welcome. Okay, guys, let's continue for the next part of this question. There are so many more to go. In the next part, we should find VCM. Listen, we have VCM. It says find the VCM in part A, and just make sure that is the VCM in this circuit greater than the next one or not. So let's find VCM. We know that VCM is a DC voltage. So for finding a DC voltage, you have to do DC analysis on the circuit. And just something else. Okay. Use across the bias current source. Okay, so listen, it says a DC voltage also appears across the bias current source. It means when you in that current source you have here, you should have, for example, a positive, negative V common source, V current source, as the voltage over that because of the given hint. So let us continue with the DC analysis. So for doing some DC analysis, you will have, this is your DC analysis. So you will have RC on the top. You will have VCM, which is only your DC voltage. RE, the other RE, something like this going, and here you have VCM again. And from here on you have a current source to negative VE, sorry, this is negative VE. And remember, the voltage over that current source is also given by V current source. So simply, guys, for finding that VCM in DC analysis, I will just do a KVL in this loop. Then I will have a negative VCM plus a base emitter voltage plus RE. And listen, what is the current passing through that RE in the loop? When you have I branching out, then you have a half I here and half I here, since that capital RE are equal. Then in your KVL, you will have the capital RE times the current plus VCS minus that VEE all goes to 0. Our job was to find VCS. So for finding VCS, let's take everything to the other side. So VCM minus VBE plus VEE minus RE I over 2. This is the voltage and current source in part A. We have to find the same in part B as well, and then compare it all together. So let us continue here. Okay, so guys, that was all about part A of the question. Now let me do the same for part B of the question. I hope that I have enough space here. Okay, again, for part B of the question, which is here, again, you should do a half circuit and then all the AC analysis to find AD and RID. And then after that, you should find the VCS, which is over the current source in DC analysis. So let me just clean it for now. So for now, I'm just working on AC analysis. AC analysis for half circuit. Okay, then you will have one RC on the top. It's right the half of this circuit, so you will have only the AC voltage source, and you will have you see you have two times of capital RE. It means one RE and another RE. Simply you can separate it and have a capital RE here as well going to 0, because all these current sources are open circuit for now. Okay, so this is only your half circuit, and if you have your half circuit here, will be also your VOD over 2. But we don't need it for now. Let's continue with our AC analysis and find the current of base, emitter, and collector. If I continue here, I will have VID2 passing here. I have RC to RE. In my Q2, I'm gonna name this by Q1 and Q2. I will have negative VID2, and up here, I'm sorry, this is going to the ground. This is also RC. And the output comes here. So positive and negative VOD. That's it. Okay, again, like what we did before, I can simply connect these 2 points, and instead of showing negative and positive, just claim that here I have VID in total. And finally, I can find VOD over VID, and also look at the circuit from the base of, change the color. If I just look at it from the base of Q1, I can find my RID. For finding each and every one of those, you first need to do current analysis. Current analysis remember, this is in AC analysis. I have IB1 here, IB2 here, IE1, IE2. If you just follow this, definitely IE1 must be the negative of IE2. Or if you have like IC1, that should be definitely opposite of IC2. IC1 here and IC2 here. So let's continue with this. Again, like what we said before, IB1 should be inverse of IB2. Doesn't work. Sorry, give me a second. Okay, now it's working. So again, I can say, I'm gonna follow over there. I'm gonna say IB1 is the negative of IB2. And it's like having the total voltage over the total I is like V over R. The total resistance from the base of Q1. So you have 2 RE and 2 little RE, all times with 1 plus beta coming to the base of Q1. 2 RE plus 2 times little RE times 1 plus beta. This is something here. And about IE1, which should be inverse of, it should be negative of IE2. Remember, IE is beta plus 1 of, so it will be, if I do just beta plus 1 of that, the ID, here I will have VID, 2RE, 2 little RE. If you do IC1 equal negative IC2, IC is beta times IB. So you will have beta VID over 2RE plus 2 little RE times 1 plus beta, and this is alpha. Alpha VID over 2RE plus 2 little RE. Okay, I think we're good here. Let me check. Yeah, I think we're good. Okay, let's go ahead and find AV, which is VOD over VID. Again, like what we did before, VOD is this point. Let me name it VO2 and here VO1. Again, VO2 is the voltage over RC when there is a current passing through RC in this direction to the ground. And that current must be in the opposite direction of IC2. That's why I will have, so like what we had before, simply you can say it is VO2 minus VO1 over this, which is negative RC IC2 minus negative RC IC1 over VID. Again, doing the rearrangements and everything, like what you had before, you will have alpha RC over RE plus the capital RE. So this is my voltage gain in the differential amplifier. Now I want to do RID, the input voltage of this differential amplifier. This is AD. So that resistance will be the total voltage which we can see from the base of Q1 over the current passing through the base of Q1. Just replacing IB1 by what we have here, you will end up having 2 RE plus the capital RE times 1 plus theta. As you can observe, AD and RID are the same as the previous case, while our circuit is totally different. So where is the difference here? Maybe the difference is around finding the VCS, the current source voltage. Okay, now let us go ahead and find the current. Let's do some DC analysis and find the current source voltage. Just by I'm not gonna draw this everything one more time. Just remember, in DC analysis, this is gone because it's an AC current voltage source, and if you do some KVL here, you will have VCM, a base emitter voltage in DC analysis. You will have this voltage and a negative VEE. That's so simple. For DC analysis. Okay, so if you do a KVL up there, you will get a negative VCM plus base emitter plus VCS, current source, voltage, and VEE all going to 0. So finding current source voltage, you will get VCM plus VEE minus base emitter voltage. This is our voltage source here, voltage of current source here, and previously I had this as the voltage of the current source in part A. As you see in part A, there is an extra term which is also negative, and that one more negative extra term makes VCS in part A more negative than VCS in part B. So that's the only reason we should say VCS in part A is more negative. So I can say circuit in part A allows more. Part A circuit allows more negative value over VCS. So that's it, and with this question. Any problem here? Raise your hand, please, if you have any question. I think we're fine. No question here? Great. Can you scroll up a little bit? Yes, I can. Let me do this and you can see better. Okay, I think I'm done with the questions here. No, one more question. So, one more of this DC differentials. Okay, let's move on to the next one. Again, next one we have differential amplifier, like what we discussed here. Okay, we have a differential amplifier here again. And for finding this differential amplifier, this is a little different from what we had in the previous cases. Why is it different? Because we have a load resistance between positive VO2 and negative VO2. That's where the problem arises. So what can we do in this kind of questions? Again, here it didn't ask me for the half circle. Forget about the half circle. Let's straightly go for finding the AC analysis. I should find the voltage gain, I mean AD, for the common mode voltage gain. As for the common mode voltage gain. Okay, let us go ahead find this. Listen, there is a difference in terms of doing AC analysis. Because, as I said, because of that RL, which you can observe over there. So in our AC analysis, you will have something like this. This is 10K. You will have this. You know that those current sources are open circuit, so you will only have 200K and that RE, which is 300 ohm, 200K again, and 10K again, and here we have RL, which is 20K ohm. So why is it different? As I said, the AC analysis will be different. You see, here we will have again VID2, here we will have negative VID2. That's all the same. But what happens to our AC analysis? If you have the base 1 here, and you know that here you will have I base 2, this is going to be your I collector 1, this is going to be your I collector 2, I emitter 1, and I emitter 2. But what happened? What is the voltage passing through 10K? Let me name this the current passing through the load. Then here I'm gonna have, let me name it I2, another current passing through the collector resistance in Q2. And let me name this guy I1. Okay, then you will need to do some KCL in point A and point B to find your their IC1 and IC2. If you do a KCL in part A, what will you get? So if you do some KCL in part A, you know that I2 is entering the node and IL and IC2 are exiting the node. Then from here, IC2 equals I2 minus the load current. That's IC2. Now, repeating KCL in node B. You know that IC1, I1 is entering the node, I1 and IL are entering the node, while IC1 is exiting it. Simply, you have your IC1. And from here, you can say that, okay, I1 will become IC1 minus IL. And later on, I'm just doing it here, but later on you will need to find I1 minus I2. So let me do it here. I1 minus I2 gives you IC minus IL minus IL minus IC2. Then finally it's like IC1 minus IC2 minus 2IL. Let's keep this, we will use it later. And remember, we know that IC1 and IC2 must be exactly, they should be in the opposite direction, but equal in size. So since we know that IC1 is negative of IC2, I can replace IC2 with another IC1, then finally I1 minus I2 will become 2 times IC1 minus 2 times IL. We can keep this one as well. Okay, let us continue. If I want to find VOD, listen, this is different. If you want to find VOD, VOD is actually the voltage difference between RL over RL, while a current IL is passing through it. So you can say VOD will be RL times IL. And from here, you can do some rearrangements and find IL by VOD over RL. And again, we know that VOD, on the other hand, is VO2 minus VO1. So if I do, on the other hand, VOD equal VO2 minus VO1, like the same thing we did in the previous examples. Oops. Like the same thing we did in the previous examples, you can say VO2 is a voltage over RC when IC is in the opposite direction of IC2. So it will be negative, VO2 will be RC times negative IC2. Negative, let me see. Sorry, it will be, the current passing through 10K is no more IC, it is I2. So for finding VO2, you're actually looking for a current passing upward. So you would say RC times negative I2. This point is VO2. This point is VO1. Okay, continuing this. So instead of, previously we had IC, but here I have RC times negative I2 for my VO2. So RC times negative I2 minus, again, same for VO1, so it will be RC times negative I1. So finally, if you just simplify it, you will have RC times I1 minus I2. I remember that I1 minus I2 also equals this. So by replacing it, let me name this equation star. By replacing equation star here, my VOD will equal RC times, or let's say 2 times RC, IC1 minus IL. And I know that IL also equals this. So if I name this equation double star and replace IL from the equation above, I will have VOD equal to RC, IC1 minus VOD over RL. You have VOD on the left side and another VOD on the right side. Let us bring it together. And finally, if you just do this, if you do some rearrangements, you will have VOD. And if you factor out VOD from both, you will have 1 plus 2RC over RL. On the other side, you will have only 2 times RC IC1. So far we got all the way up to here. But so this is IC1. And I know that there is a relation. I actually didn't write this part, but we all know that there is a relation between IC1 and IB1. IC1 is, let me write it here. Guys, we all know that IC1 is beta times IB1. So if you just replace it by beta times IB1, then finally we will be able to replace IC1 with something in terms of IB1. So instead of that, I'm going to write beta times IB1. Then if you do some, and what is, actually I forgot to find my IB1. So far it's all good, but I forgot to find my IB1. I need to find it, yes. Again, I need to find IB1. How can I find my IB1? If you look at this circuit, like the same way we used to looking at the circuits, if you imagine that here you only have the ID, and now you're looking at the circuit from the base of collector 1, then you can simply say that our ID equals the ID over I base 1. But I'm more interested in finding I base 1. Then if I do some rearrangements, I base 1 will become the ID over the resistance being shown, being observed from the base of Q1. And the resistance that you can observe from the base of Q1 will be simply that RE times that little re times 1 plus beta. So it will be 2 times Re plus that capital Re times 1 plus beta. And if I take this all down, if I replace IB1 here, so finally I can have 2 times of RC beta. Instead of IB1, I'm going to replace it with what I had above, the ID over 2RE plus that capital RE times 1 plus beta. Remember again, let me put it on the top of here. Remember, beta over beta 1 plus beta also equals alpha. So it means you can show the total left side of equation by 2RC VID alpha over 2RE plus the capital RE. And this all equals to VO 1 plus 2RC over RL. Okay, finally, finding VOD. This is VOD. Finding VOD versus VID, it will be just some simple rearrangements. So VOD over VID, you just need to do some rearrangements, and finally, I think I need to do this because I don't have the final answer. So it will be 2RC alpha over this over RL plus 2RC over RL. So finally, it will be 2RL RC alpha over 2RE plus that capital RE times RL plus 2RC. I think this is it. That's the last. Yes, that's it. So we found the voltage gain here as well. Guys, it is it's already 11. Class time is up. Let's meet in 15 minutes if you have any more questions in the office hour time. Sorry, I really need to take some break because it took so much energy
Can
from
you
me.
quickly, can you just quickly then, if for us who can't go to the office hours, can you quickly scroll down so we can see what the other questions were?
That's a good question. The other question were only question 1 and 3 from assignment 3. That
Oh,
I
so,
used,
so they're
yeah,
the okay.
I did this in the previous tutorial. You have it.
Okay, because you didn't post, you hadn't
Of course,
posted
yeah.
yet.
Right after the class, I'm gonna post this, and
Okay.
I'm gonna post a previous tutorial as well. Guys, thank you very much. I will see you in office hour in a short time if you have any question.
I
Thank you.
just
See
have
you
a.
soon. Bye bye.
When's your office hours? Sorry.
It will be in 15 minutes. Starting at 11:15. I
It's
just
the
need to
same
take
link,
some break.
right?
Okay, okay.
Yeah, same link, same. Be back soon.
Can we just stay here then? And
Yeah.
okay.
Oh, yeah. Depends on you. I will be back.